Okay. So I said that we are considering homogeneous space of this group. On the homogeneous space of this group, we have a well-defined, we have a foliation which is preserved by the group action. The leaves are modeled on the uni-modular-like geometry. We ask whether the J action preserves, preserves a Lorentzian metric on X. Okay, so here I will take a subgroup of, to make it simple, I take a subgroup of the full group, so I remove the compact part. In fact, this group already acts transitively. And so I consider like an R extension of the Heisenberg group of dimension 2n+1, which acts through a one-parameter group of automorphisms of Heis, which we can write this way, exponential of some derivation. So the isotropy here is a some abelian subgroup of the Heisenberg group of dimension n. When does J preserve a Lorentzian metric on the quotient space? So J preserves a Lorentzian metric on the quotient is equivalent to the fact that the adjoint action of I of the isotropy on the quotient of the Lie algebras preserve a Lorentzian scalar product on this quotient. Okay, so if I have a Lorentzian scalar product Q on this quotient, which is preserved by the adjoint action of I, so I can translate Q on the whole X by the left action of J. And since the adjoint action preserves this, the right action of I preserves this this quadratic form, so it will be well defined on the quotient. So the fact that J preserves the Lorentzian metric on the quotient translates exactly this way, in this way. And in our case, this is equivalent to saying that now we consider the adjoint action on the Lie of an element of the Lie algebra of the isotropy. This translates into the fact that this is Q symmetric with respect to Q. And if we look at the adjoint action of any element H in the isotropy, if it is in Heis is two-step nilpotent, so the adjoint action will be two-step nilpotent. If it is in R, if I take an element T in R, I apply the add action of H. I get an element which is in Heis. And then when I apply again twice, because Heis is two-step nilpotent, I get 0. So any element H in the Lie algebra of the isotropy is nilpotent of degree 3. And we have this general fact, classical fact for nilpotent non-zero endomorphism of a vector space. So such a nilpotent non-zero endomorphism of a vector space E is an infinitesimal isometry of some Lorentzian scalar product. So this means that when I take the exponential of this on the morphism, I have an isometry of a Lorentzian scalar product. So this is true if and only if the degree of nilpotency is exactly has a degree exactly 3, and in this case, the vector space will decompose into the direct sum of a three-dimensional subspace on which f is 3 nilpotent, and another space which is Q orthogonal on which the action is of f is trivial. So this is non-Riemannian in infinitesimal isometry of a Riemannian scalar product. If it is nilpotent, then it is, since it is semi-simple, it will be trivial. So a nilpotent non-zero endomorphism does not happen in the Riemannian setting, it happens in the Lorentzian setting. And the fact that the adjoint action has degree exactly 3 will give some restriction on L, which we write like this. I'm not given the exact the final shape of L, but the fact that J preserves, so not all so two things, not all J actions preserve Lorentzian metric on the quotient. So L has to satisfy some condition, but this condition is open. So this condition implies in particular that this derivation, when applied to A plus, to the isotropy, it is mapped transversely to itself, to the isotropy. And in fact, in dimension 3, it is the condition to preserve in a Lorentzian metric is exactly this one. In higher dimension, we have we have more restriction. Okay, so the case which is interesting for us is when we have this additional geometry on the quotient, when J preserves a Lorentzian metric on X. When this is the case, this metric is unique up to isometry, and this is exactly what we call this is exactly the homogeneous one simply connected plane waves. The homogeneous spaces we describe this way are exactly what we call plane waves. I will give it the classical definition later. On this basis, I have the action of the center of Hayes generates a null vector field V, which is parallel. Okay. When it preserves a Lorentzian metric, I have a well-defined null parallel vector field parallel with respect to the Levi-Civita connection of the Lorentzian metric. So what do I have now? I have a homogeneous space on which I have a parallel null vector field defined by generated by the action of the center of Heisenberg group, and the orthogonal of the distribution, which is orthogonal to V, defines this foliation I gave before, which is modeled on the affine unimodular light-like geometry. Okay, so examples. Trivial example is just Minkowski spacetime endowed with on which I consider a null parallel vector field. So the subgroup of the isometry group preserving a null parallel vector field, if I compute, it is exactly this one, where K here is the whole group ON. Well, I will come back to this example later, so let me skip this. So among these spaces, we have what we call oscillator group. How is it defined? I consider a Heisenberg group of dimension 3, extended by R. So how does R act on Heis 3? It acts trivially on the center of Heisenberg, and it acts by a rotation on the quotient space, on Heis, on the quotient of Heis by the center. It acts by a rotation. This is a Lie group, and I consider a basis of this Lie group, of the Lie algebra. So T generates the first R factor, V generates the center of Heisenberg, and XY generate the supplementary of the center in Heis. And I consider this Lorentzian scalar product on the Lie algebra. So I make T and V both isotropic with their scalar product equal to 1, and the R factor and all these factors are sorry. The subspace generated by T and V orthogonal to R2. The supplementary of the center in Heis. This is a Lorentzian scalar product on the Lie algebra. I can define it everywhere by translating by J. And in fact, this will define a Lorentzian metric on J, which is B invariant. And since it's B invariant scalar product, I have J times J, which acts. I have J which acts isometrically both on the left and on the right. So the full isometric group will be bigger than J. It will be, it's J times J, the quotient of this by diagonal of the center, and I get exactly something like this. So J here is a Lie group inside this bigger group, on which I have a plane wave metric. Another example, which is not a Lie group, you can find it in the paper of on three-dimensional plane waves, homogeneous plane waves, by Zeghib, Abdurrahman al-Qasim, and Ghani Zeghib. Here, the group is the same. Well, no. I have an R extension of Heis 3, but here R acts by an homotopy. Here, before R acted trivially on the center. Here it acts by an homotopy on the center. And on the quotient space, it acts by a similarity. So a rotation and an homotopy on the quotient space. Here I have the action of I take any one-dimensional subgroup here, which is different from the center. It preserves a Lorentzian scalar product on X. And this example is not a Lie group. There is no three-dimensional subgroup here, which is transversal to the anisotropy. Okay, so for this question on standardness of these homogeneous plane waves, we prove the following. So here we call the group, and I call P the projection to the first R factor. We prove the following. When the projection of gamma is dense in R, this corresponds to the case where okay, what is this F? Okay, remember that on the quotient on the homogeneous space X, we have a null parallel vector field defined by the action of the center of height, and if I consider it's orthogonal, it defines this foliation, which is totally geodesic foliation, which is generated by the action of k semidirect height. This foliation, I call it F. The case where gamma has a dense projection in R, all the leaves, this corresponds to the case where all the leaves are dense in the quotient M at gamma. In this case, we prove that any compact quotient X is standard. More precisely, we prove that gamma is a co-compact lattice in a connected nilpotent closed subgroup N of J, which acts freely transitively. When the quotient, when the projection is discrete, here we can have non-standard examples. But we have the structure of gamma. It is a cyclic extension of some discrete subgroup contained in height. And the Zariski closure of this gamma 0 in height acts freely transitively on the leaves. In this situation, we have no standard examples. Okay. So I'm going to give an outline of the proof. Before this, some comments. The case where the homogeneous plane wave is compact, it corresponds just to the data of the Minkowski space together with some isotropic vector. In this case, J is exactly this group here, where K here is the full orthogonal group. So this situation can be compared. This situation is already done. Is contained in the Lorentzian in the result by Goldman and Fried. And we know that in this case there is a synthetic hole. But to compare with this flat case here, the semi-simple part in this group, K here is just the orthogonal group of a Euclidean scalar product. It's ON. Whereas when we consider the full group reserved in the flat Lorentzian metric, we had O1N. So the semi-simple part here is easier than in the general flat Lorentzian case. But for our homogeneous plane waves, which are non-flat, the semi-simple part is easier than the semi-simple part is easier than in the case of a flat Lorentzian manifold. But what we lose is that we lose the algebraic structure of the group. Here, the action of R can be almost anything. And J is not an algebraic group, so we cannot apply the algebraic tools, the algebraic arguments used by Goldman and Fried in their proof. Okay, so what yeah, before going to the proof, let me also point out that when the action of R here is well, there is a subfamily of these plane wave metrics, which we call Karen-Vallar spaces, which are exactly the plane waves which are globally symmetric spaces. And for those spaces, the R action on the Heisenberg group is semi-simple. In this case, this case is studied by Ines, Kath, and Martin Ulbrich, and they prove the existence of, they study the standardness question, and they prove a theorem analogous to this one. But it turns out that in the general case, the R action can be anything I said, and the proof does not, to generalize the proof from this semi-simple action to general action is not easy, and the arguments do not adapt. So what saves us here is a result, is a very beautiful lemma, which we call Zeichenhaus lemma. I forgot to say that this theorem is joint work with Malek. He's here. His PhD advisor, Ines, Kath, and Ghani Zeghib. Okay. So, Zeichenhaus lemma. Let J be a Lie group. For Zeichenhaus lemma ensures the existence of a neighborhood view of the identity element of J, such that any discrete subgroup generated by elements in U is nilpotent. You can find this version in the book of Raganutan. But we have more than that. We have a stronger result, which we call strongly Zeichenhaus neighborhood, which states that we have a neighborhood of the identity such that any discrete subgroup gamma which is generated by elements in U is in fact a uniform lattice in a closed connected nilpotent subgroup of J. So this is more than this. Here it says that we have a synthetic hole of gamma which is nilpotent inside J. And this version of the theorem is, you can find it in Thurston's book on geometric structures. Okay, so now that we have this powerful lemma, how the proof is, how does it go? Just an outline of the proof. So I said that gamma in any Lie group, a discrete subgroup which is generated by small elements, will have a synthetic hole, which is nilpotent. Now, here we have gamma. What is, I consider P to be the projection to the R factor and R to be the projection into R times K. So is gamma, can gamma be generated by small elements? So any element gamma in this group can be written RKH, where R is the R component, K is the component in K, and H is the component in Heisenberg. I want to know if gamma can be generated by small elements. So first I will care about the RK component. Can I choose generators of gamma such that the RK component is small enough? What captures the small RK, the elements with small RK component? I project the group gamma in R times K. So and I take the closure, this group I call big R, and I look at the connected component of this group. Okay, the connected component of this group, which we call it the non-discrete part of this projection. In fact, the elements of gamma which project in the connected component here, in the connected component of R, are exactly the elements of gamma which can be generated with is exactly the subgroup of gamma which can be generated by elements that have small RK component. Okay, because the identity component, the projection of gamma is dense in the identity component here. So it can be generated by any small element. And it will be also the case for if we take the pre-image of this group by R inside J. So the question, I forgot to say that all this standardized question, in fact, is considered on gamma up to finite index. So gamma is standard if there is a finite index subgroup which has a synthetic hole. So we only care gamma up to finite index, which topologically corresponds to taking a finite cover. So here, if the identity component of R, if R has finitely many connected components, then I'm sure that I can find a finite index subgroup of gamma, which can be generated by elements which have a small RK component. And this happens exactly when gamma has dense projection to R. When gamma has dense projection to R, this the set here has finitely many connected components, and I can find a finite index subgroup in gamma, which is generated by elements which have small RK component. This phase when the projection of gamma to R is discrete. In this case, R has infinitely many connected components. So I will follow with the case where the projection is dense. So in this case, I said that gamma, there is a finite index subgroup of gamma which can be generated by elements with small RK component. And then I still have this H component here. The idea for the H component is that the Heisenberg group has a one-parameter group of homothéties. Okay. It has a one-parameter group like we have on Rn, we have homothéties. On Heisenberg group, we have also a one-parameter group of homothéties. Homothéties transform big elements to small elements. So I will apply, I will define isomorphism of this group, applying a suitable homothéty of Heis in order to transform the big H elements into small ones. And this way I can ensure that my that gamma is generated by elements with small components. This I said that this is the case when the projection on the R factor is dense. Otherwise we have this split exact sequence, and in fact we can prove that the projection here is discrete, so this is isomorphic to Z, and here we can prove that the intersection of gamma, not of P of gamma. Intersection of gamma with this group is in fact contained in the Heisenberg group. Here we can find non-standard examples but okay, this is for the proof. The fact that it acts simply transitively, it's the same idea as the fact that the synthetic hull in this case, in the first case here, acts simply transitively. It's the same idea as in the flat Lorentzian case. It's because it's related to the geometric dimension of gamma, which is here exactly n, the dimension of the manifold, and when such gamma acts, when a discrete subgroup gamma of any group acts co-compactly on a contractible manifold, I said that it acts transitively. Okay. So here I will give the general context of those plane waves metrics, plane waves manifolds. They belong to marginal spaces that we call Brinkmann spacetimes. So Brinkmann spacetime is a Lorentzian manifold which admits a parallel null vector field. The interpretation via the holonomy is that the holonomy group at some point preserves some isotropic vector. So in the tangent space, so if I have this V, which is preserved by the holonomic group, I parallel translate V everywhere. I have a well-defined vector field, which is by definition parallel, and which is isotropic. And these spaces belong to what we call spaces with special holonomy. This means that here the holonomy group admits an invariant subspace, but here the metric induced on this subspace is degenerate, so I do not have a splitting of the tangent space, and the metric is not locally product. Our aim is to understand these Brinkmann spaces. Okay, so here, when I have a Brinkmann space, V is a Killing vector. So this parallel vector field induces one parameter group of isometries. The parallel distribution is, the orthogonal distribution is parallel, so it is integrable, and it defines the foliation, codimension 1 foliation, which in the case of plane waves was given by the action of the Heisenberg group. Special cases of Brinkmann spacetimes are given by what we call PP waves. PP waves are Brinkmann spacetimes for which these leaves are flat. The leaves are totally geodesic, so they have an induced connection. And it is a PP wave when the leaves are flat. And as a subclass of these PP waves, we have these plane waves spaces. But the original definition of plane waves is the following. So plane waves are PP waves which are almost symmetric. So we have this condition. And the metric locally, we have coordinates in which the metric takes this form. So PP waves and plane waves are special classes of Brinkmann spacetimes obtained with conditions on the curvature. And in the opposite direction, we have generalizations of this. We have Kunt spacetimes, which are Lorentzian manifolds with a codimension 1, like geodesic foliation. The plane waves are studied essentially from the physical point of view, and beside this definition of plane waves, we have a characterization of plane waves in terms of the Lie algebra of killing fields that act on plane waves. And Blow and Loveland prove that that plane waves are characterized among Brinkman spacetimes by the fact that they contain Heisenberg, by the fact that the Lie algebra of Killing fields contains a Heisenberg algebra which acts transitively on the leaf on the leaves of this foliation. What I considered before was were sorry, what I considered so far were homogeneous plane waves. But in general, plane waves have cohomogeneity 1. It means that the isometry group will span some codimension 1 foliation. Something that we did about the general plane waves is to give some synthetic description. I try to give it very quickly. So let us come back to this to the Heisenberg group. On Minkowski space, we have the dimension n+2 endowed with this metric. I have isometric action of the Heisenberg group. So Heisenberg is contained in the isometric group. How does it act? Remember that the Heisenberg group is an extension of Rn+1 by Rn. Rn+1 acts by translation. So on the Vx coordinates and trivially on the U coordinate. So here it acts by preserving this vector V, this null vector V. And Rn acts by this unipotent transformations. It's a linear action. This action of Heiss preserves the vector V. It preserves, I said it before, it preserves the affine unimodular light-like geometry on the, okay. This, in fact, this action of the Heisenberg group preserves the foliation of Minkowski space by these hyperplanes. This action acts, the Heisenberg group acts trivially on the U coordinates, so it preserves these hyperplanes. And on each hyperplane, it acts by preserving this affine unimodular light-like structure. The action of the Rn+1, the translation structure is constant with respect to U. And the action of Rn, if I let this matrix here act on an element Vxu of Minkowski space, I have this, it acts this way. The U coordinate is preserved. And on the affine hyperplane Vx, it acts by this affine transformation, which depends on U. Remember that when U equals 0, though I do not have this vector here, we called this, this action is exactly what we call the usual action of Heisenberg on Rn+1. So on the other levels, when U is not 0, this action is deformed by a translation vector. So the Heisenberg group acts on these hyperplanes by preserving this geometry, which we call the affine unimodular light-like geometry. And I can so on each hyperplane, I have an action of the Heisenberg group, and from one hyperplane to another, in fact, I can write this action using some curve in the automorphism group of Heisenberg. So I take an element Vxu in Minkowski space, an element H in the Heisenberg group. I let H act in the following way. So U is preserved, and the action of H on Vx depends on U. And it is, I can, in the case of Minkowski, I can write this action using some curve in the automorphism group of the Heisenberg group, which is exactly this one. And in fact, here I'm just writing the fact that inside the isometry group of the Lorentz group, I have an extension of Heisenberg group, which, so I have R semi-direct Heis, which acts isometrically on Minkowski spacetime. And now if I consider exactly this, I consider an action like this here, written in the same way, but now I let this curve here, so this curve which deforms the action of Heisenberg from a hyperplane to another, I let it be any curve in the automorphism group of Heisenberg. And I start with some representation, with some action of Heisenberg which preserves this structure. And I deform it with any curve in the automorphism group of Heis. The fact is, well, first, not any action like this preserves a Lorentzian metric on Rn plus 2, okay? But when it does, when an action, when there is a Lorentzian metric preserved by this action, we get exactly plane waves, the simply connected plane waves, well, which are not homogeneous. And the homogeneous plane waves correspond exactly to the case where the curve here, this curve here, is a one-parameter group in the automorphism group of Heis. And here I get the subgroup of G0 I wrote before, which is R semi-direct Heis, which is the isometry group of a homogeneous plane wave, simply connected plane wave. Okay, so the way we describe plane waves from the way to pass from the original definition to this in description of plane waves using this cohomogeneity one actions of Heisenberg. We use here many things. So we use first that we have an infinitesimal action of the Heisenberg algebra, which is a result by Plo, and we prove that. Okay, in fact, in general, for if I consider any simply connected plane wave, it's not true that I can always get it a description in this way. There are some completeness issues that come into play, and if I can integrate this action of the Lie algebra into an action of the group, I can get a description like this. Okay. So the interest of for in the case of homogeneous plane waves of one of the interest of the standardness question is we can apply it to study the dynamics of V. But this question has a sense in the full general setting of Brinkman spacetimes. So we have, if we consider a compact Brinkman spacetime with a null parallel vector field, we can ask whether this action of V preserves a Riemannian metric on M, or which is equivalent to saying that the flow of V inside the assumption group generates is relatively compact inside the assumption group. In the case of homogeneous plane waves, when we can reduce, when we know the position of gamma, when we know that gamma is a co-compact lattice in some connected Lie group, which acts simply transitively, so the space will be the compact manifold M will be the quotient of a left invariant metric on a Lie group by a lattice. And in this case, the study of the dynamics of V reduces simply to is an easier question. It reduces to the equicontinuity of a left invariant parallel vector field on a Lie group endowed with a left invariant Lorentzian metric. And this is an easier question than the general one. But one can ask in fact, for general Brinkman spacetimes, we prove that this question of the dynamics of V reduces to exactly to the homogeneous case or to the cohomogeneity 1 case. In the cohomogeneity 1 case, we know that this action preserves a Riemannian metric. So the left and the question is still open in the homogeneous case. But for homogeneous plane waves, which is a subfamily of Brinkman spacetimes, the V preserves a Riemannian metric, and the question is still relevant in the general Brinkman spacetime. Okay, so I stop here. Thank you.